Hi everyone, here we are going to see about the unit 4 continuation part. So let me see the continuation. Next is h of z. So there is a s naught into b naught plus b1 z inverse plus b2 z power minus 2 divided by 1 plus a1 z inverse plus a2 z power minus 2. So that is known as s naught into n of z by d of z. So from the figure we can analyze that h dash of z is equal to w of z divided by x of z, that is equal to s naught by 1 plus a1 z inverse plus a2 z power minus 2, that is equal to s naught by d of z. So w of z is equal to s naught x of z divided by d of z. So that is equal to s naught s of z into x of z. So where s of z is equal to 1 by d of z. So we have w of n, that is equal to s naught by 2 pi integral s of e to the power of j theta x e power j theta into e to the power of j pi theta into d theta. So w of n the whole square is equal to s naught square by 2 pi squared integral s of e power j theta by x of e power j theta into e power j pi theta into d theta, the modulus of squared. So using the Schwarz inequality, w of n squared is less than or equal to s naught squared. So that is integral 2 pi modulus of s of e power j theta squared into d theta. So that is integral 2 pi into x e power j theta the whole square d theta. So applying the Parseval's theorem, w of n squared is less than or equal to s naught squared. So summation n equal to 0 to infinity x squared of n 1 by 2 pi integral 2 pi into s of e power j theta the whole square into d theta. So if z is equal to e power j theta, then dz is equal to j e power j theta into d theta. So which will give d theta, that is equal to dz by jz. So by substituting all the values, w of n is squared is less than or equal to s naught squared summation n equal to 0 to infinity x squared of n into 1 by 2 pi integral 2 pi f integral close integral s of z squared z power inverse dz. So w of n squared is less than or equal to s naught squared summation n equal to 0 to infinity x squared of n 1 by 2 pi f integral s of z inverse into dz. So w square w of n squared that is less than or equal to summation n is equal to 0 to infinity x squared of n into x squared of n when s naught squared 1 by 2 pi f integral s of z into s of z inverse into dz is equal to 1. So it will give that s naught squared is equal to 1 by 2 pi f integral z inverse dz by d of z inverse. So that is s naught squared is equal to 1 by I. So where I is equal to 1 by 2 pi j integral c. Next that is z inverse dz by d of z inverse. So we have to note that the process of scaling the overflow is eliminated here. So the scaling factor will be the first stage. So that is the scaling factor for second stage is s naught 1, and it is given as s naught 1 squared is equal to 1 by s naught squared into I2. Okay, so here I2 is equal to 1 by 2 pi f closed integral h1 of z inverse divided by d2 of z inverse into dz. So for the given transfer function, the h of z is given. Find the scaling factor so as to avoid the overflow in the adder 1 of the filter. So the diagram is given. So first we have to write the given values. So that is d of z is equal to 1 minus 0.5 z inverse, and d of z inverse is equal to 1 minus 0.5 z. So that is I is equal to 1 by 2 pi close integral 1 by d of z inverse z dz by z. There is a we have to substitute the values, then we get a residue of z by z minus 0.5 into 1 by 1 minus 0.5, that is z is equal to 0.5. So I is equal to, we will get the answer. So s naught is equal to 1 by root of 1, s naught is equal to 1 by root of 1.333, that is 0.866. So consider the recursive filter shown in the figure. That is the input x of n as the range values of plus or minus 100 volt, and it is represented by 8 bits. So we have to compute the variance of output due to analog to digital conversion process. So there is first we have to write the solutions. So there is given ranges, that is plus or minus 100 volts. Difference equation of the system is that equation whose impulse response h of n can be obtained as h of n is equal to 0.8 power n u of n. Okay, so next quantization step size is n equal to range of the signal by number of quantization levels. So 200 by 2 power 8, so we'll get the answer as 0.78 to 125. So variance of the error signal is sigma e squared is equal to q squared by 12. So we have already find the q square, so q value, so we have to substitute that to find out the sigma e square. Next we have to find out the variance. So sigma e squared is equal to sigma e squared in summation n equal to 0 to infinity x squared of u. So substituting these values, we will get the output answer as 0.14128. Next question. The input to the system y of n is equal to 0.999 y of n minus 1 plus x of n is applied to an ADC. What is the power produced by the quantization noise at the output of the filter if the input is quantized to 8 bits, 16 bits? First, we have to write the y of n equations, that is 0.999 y of n minus 1 plus x of n. Taking the z transforms on both sides means there is y of z is equal to 0.999 z inverse y of z plus x of z. So that is h of z is equal to y of z by x of z. So 1 by 1 minus 0.999 z inverse. So next we have to equate that h of z into h of z inverse into z inverse equal to z by z minus 0.999 into z inverse by z inverse minus 0.999 into z inverse. So that is z inverse divided by z minus 0.999 into minus 0.999 into z minus 1 by 0.999. So then we will get the next value as output noise power due to the input quantization, that is sigma s I squared is equal to sigma 1 by 2 pi sigma squared by into 1 by 2 pi j into closed interval h of z inverse into z inverse dz. So when we are substituting the values, I is equal to 1 to n, residue of h of z inverse z inverse, that is z equal to pil. So where p1, p2, etc. up to n are poles of h of z inverse that lies inside the unit circle in z primes. So sigma SCI that is equal to sigma e squared z power p minus 0.999 into 0.001 by z minus 0.999 into z minus 0.001. Limit is z is equal to 0.999. So we will get the value. So that is b plus 1 is equal to 8 bits, assuming including sign bits. So b plus 1 is equal to 16 bits, assuming that we have the values. Find the effect of coefficient quantization on the pole locations of the given second order IAR system. So when it is realized in a direct form 1 and in cascade form, assume the word length of 4 bits through the truncation. So that is h of z is given 1 divided by 1 minus 0.9 z inverse plus 0.2 z inverse. So first we have to form the direct form 1. So let b is equal to 4 bits, that is including the sign bits. So 0.9 is equal to, we have to convert it to the direct form. So there is integer part 0.9 into 2 by 1.8 and 0.8 into 2 by 1.6, 0.6 into 2 by 1.2. 0.2 into 2 by 0.4, 0.4 into 2 by 0.8, 0.8 into 2 by 1.6. So after the truncation, we will get the 0.111. So that is 0.875. So 0.2 means 0.00110 020. Okay. Next for 0.2 we get 0.2 into 2 by 0.4, that is 0. 0.4 into 2 by 0.8, that is 0. 0.8 into 2 by 1.6, 1. 0.6 into 2 by 1.2, 1. 0.2 into 2 by 0.4, that is 0. After truncation, we get the 0.001 is equal to 0.125. So this system truncation function after coefficient for quantization, there is h of z is equal to 1 divided by 1 minus 0.875 z inverse plus 0.2125 z power minus 2. So now the pole locations are given by z1 value is 0.695 and z2 is 0.178. So if we compare the poles of h of z and h bar of z, we can observe that the poles of h bar of z will derivate very much from the original poles. So this is the direct form. Sorry. Next we are going to see about the cascade form. So that is h of z is equal to 1 divided by 1 minus 0.5 z inverse into 1 minus 0.4 z inverse. So that is equal to 0.1000. After truncation, we will get 0.100 is equal to 0.5. So this we get 0.011 is equal to 0.375. So likewise we have to get the answer. 0.4 means 0.4 into 2 by 0.8, that is 0. 0.8 into 2 by 1.6 is 0. 0.6 into 2 by 1.2 is 1. 0.2 into 2 by 0.4 is 1. 0.4 into 2 by 0.8 is 0. So the system function after the coefficient quantization is h of z is equal to 1 divided by 1 minus 0.5 z inverse into 1 minus 0.375 z inverse. So the pole locations are given by z1 is equal to 0.5. z2 is equal to 0.375. On comparing the poles of the cascade system with the original poles, we can say that one of the pole is same and other pole is very close to original pole. Okay. Next question is, an LTI system is characterized by the difference equations. So there is y of n is equal to 0.68 y of n minus 1 plus 0.5 x of n. The input signal x of n has the range of minus 5 volt to plus 5 volt. So represented by 8 bits. Find the quantization step size, variance of the error signal and variance of the quantization noise at output. So here we have the given, first write the given values, that is range R is equal to 5 volt to plus 5 volt, minus 5 volt to plus 5 volt. So there is 5 minus of minus 5 is equal to 10. Size of the binary is 8 bits. Quantization step size is Q is equal to R by 2 power 8. So 10 by 2 power 8 we will get the answer. Next we have to find out the variance. So that is the sigma is squared is equal to Q squared by 12. We have find the quantization value. So Q squared by 12 we have put, we will get the answer. So the difference equation governing the LTI system is y of n is equal to 0.68 y of n minus 1 plus 0.15 x of n. So on taking the z transform on both the sides, we get y of z is equal to 0.6 z inverse y of z plus 0.1 sorry 5 x of z. So that is y of z is minus 0.06 z inverse y of z is equal to 0.15 x of z. So that is y of z is into 1 minus 0.6 z inverse is equal to 0.15 x of z. So y of z by x of z is equal to 0.1 by 1 minus 0.6 z inverse. So So that is h of z is equal to y of z by x of z. So 0.1 by 1 minus is 0.68 is z inverse. So h of z inverse into z inverse is equal to 0.1 by 1 minus is 0.68 is z inverse plus into 0.1 by 1 minus is 0.68 is z inverse into z inverse. So that is we have to consolidate the values. So we get the h of z and h of z inverse is z inverse values. So now the poles of the h of z inverse are P1 is equal to 0.68 and P2 is equal to 1.4706. So here P1 is 0.68, only the poles that lies inside the unit circle is Z plane. So the variance of the input quantization noise is at the output. So now we are going to see about the analog to digital conversion. So the analog to digital conversion has three process: sampler, quantizer, coder. So here we have passing the x naught of t and x of n, xq of n, and then we will get the digital signals. So first signaling sampling means sampling is the conversion of continuous time signal into the discrete time signal. So it should be obtained by taking the samples of continuous time signal and discrete time instance. So if xa of t is the input to the sampler, means the output is x of n ta is equal to x of n, where t is called the sampling intervals. Next quantization is we have to quantize the values of a sampling signal x of n into xq of n. So that is the discrete time signals will be quantized into the particular part and we get the output. After this quantized output is passed into the coder. The coder will be differentiates the digital values and binary to digital and digital to binary, and then we get the digital output units as zeros and ones. Okay, next let me see other topics in the next class. Thank you.